Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today we embark on an ambitious task to estimate a quantile regression in Excel. Quantile regression is a handy and flexible data analysis tool that has been proposed by Roger Koenker in the 1970s. It has been extensively developed ever since. The logic of the quantile regression is to generalize upon and depart slightly from the concept of a simple linear regression and estimate not the conditional mean of your response or dependent variable y, subject to or conditional upon some realizations of your input variables or exogenous variables x, but rather to estimate conditional quantiles. For example, conditional median, conditional 5th percentile, conditional 95th percentile, whatever you wish. And you can already imagine how important and useful this can be for risk management and stress testing. For example, if you have got data on stock returns and some benchmark or risk factor returns. For example, here we have got 5 years worth of daily returns for ExxonMobil, a large US-based oil manufacturing company. And as our exogenous X variables, we have got data on daily market returns, represented by the S&P 500 benchmark, and daily crude oil returns. You could estimate a stress testing scenario. For example, what is going to be a 5th percentile, so 5th% of lowest returns, subject to particular market and oil returns. What is the mathematics behind such estimation, though? Well, here it's all quite beautiful and intuitive. Koenker has proposed to modify the loss function of a simple linear regression, and if you recall that the simple linear regression is also called OLS, ordinal least squares, you can immediately say that the loss function of the simple linear regression is quadratic. You minimize the sum of squares of deviations from the actual value of your response variable, and this minimizes and this estimates the conditional mean, that is the center point of linear regression. Well, Koenker has showed that if you rather minimize absolute deviations, you estimate conditional median. And more generally, if you use the so-called check loss function, rho subscript tau, where tau is any quantile from 0 to 1, so 0th percentile being the lowest realization, 1 being the, or 100% being the highest possible realization, and 0.5 or 50% being the median, you can estimate any conditional quantile. What is the functional form of rho subscript tau, though? Well, the rho subscript tau of some argument a is simply the maximum of two expressions, tau times a or tau minus 1 times a. And the reason for why it is called the check loss function is the form its graph takes. So let's see it for ourselves. Let's here input the check loss function values for some range of arguments a. Here we abstract from the forecast we want to establish, the model we want to do. We just want to see what is the shape of this particular function. So for a quantile tau equal to 0.5, the median, we can start inputting our check function. So the maximum of tau rho locked times a and tau minus 1 times a. And then we can bottom right click it all the way down and get the symmetric absolute value function, which is the function that gives you, if you optimize the loss function, if you minimize that, the conditional median. And if you change your quantile to another value, for example 0.25, we can see that the function is no longer symmetric. It now has a steeper slope in the negatives than in the positives. It would mean that now it does penalize over predictions to a greater extent than it does penalize under predictions. And that is exactly what, as Koenker proved, gives you a conditional quantile of your liking. If you apply an asymmetric absolute loss function, then as a result of your optimization, you would arrive at a conditional quantile you desire. And if we change our quantile to something higher than 0.5, for example 0.75, we can see that it is again asymmetric but in the other direction. It now penalizes under predictions to a greater extent it penalizes over predictions. That would give you a quantile that is higher than 0.5, that is higher than the median. So let's now change it back to 0.5 and estimate the conditional median of ExxonMobil returns, conditional on particular market and oil returns, given our data and using quantile regression. First of all, let's input our starting values of coefficients to be zeros and start calculating our forecasted values of the y of the response variable, our prediction errors, our losses as per the check loss function, and see where it takes us. So the forecast value of ExxonMobil returns can be simply calculated as a sum product between the coefficients with rows locked, as we don't want the coefficients to change as we move throughout our sample, and the variables we have got here. For convenience, we have got a column of ones to represent the constant, and that is crucial both for the current calculation and, most importantly, for the calculation of the covariance matrix and the standard errors. So we can enforce this formula and get our forecast over here. And then we can calculate our prediction error, as in the loss function, by subtracting the forecast from the realized values of the y variable. So we just calculate the differences over here. And then we apply the check loss function to calculate the loss, the asymmetric absolute deviation from the true value of y. So here we input this functional logic, the maximum of two values. So the maximum of tau times the error and tau minus 1 times the error. And we log the row for tau and don't log the row for the error for obvious reasons. And here we can apply the loss function for all of our observations and calculate the total loss as the sum of all loss observations. And we get a total loss of 7.79. Now we can optimize it, minimize it, by changing the coefficients, the parameter values, to arrive at the optimal parameter values for the conditional median estimation. And for that, we can go data solver and specify our optimization task. We want the total loss to be minimized by changing our three coefficients. And then we need to untick the non-negative restriction because some of those coefficients can be negative, why not? And we can stick with the gradient descent, GRG nonlinear, click solve, and wait until the optimization task arrives at an optimal solution. And it has just converged to 1, and we can see that the conditional median equation has a slightly negative constant, so other things held equal, if your market return and your oil return are zeros, then the median return of ExxonMobil would be slightly negative, 14 basis points. The market beta is 0.8 and the oil beta is 0.26, which is quite realistic if you compare it to some results you could obtain from simple linear regression, for example. However, how one might calculate the standard errors for such a regression if you would have applied Linus or even a linear regression using matrix multiplication, it would have been very straightforward. However, for the quantile regression, it is a little bit trickier. Here, Koenker and following researchers in the area have proven that you could use asymptotic theory to calculate the covariance matrix for the quantile regression estimators in the following way. We have got our usual suspect, the inverse of the xt times x matrix on the right-hand side. There are no surprises here. This is something that goes into pretty much any covariance matrix specifications in linear regressions. However, on the left-hand side, we have got this adjustment term that has got tau times 1 minus tau in the numerator and squared probability density function of the error distribution evaluated at the quantile of interest. Well, the numerator is quite intuitive and easy to calculate. This is something that is estimated for many regression models where you are interested in a particular quantile or a particular probability. For example, you have got similar adjustments in probit and logit models. However, the denominator is what can be quite tricky. How to estimate the density function of your error distribution, which is this particular distribution, at the quantile we are currently interested in. Well, here kernel density estimation can be called to the rescue. And we have got a separate video on kernel density estimation if you are interested in just that, but here we will briefly use it to estimate our covariance matrix. Well, here we simply need to calculate the sample size, which is the number of observations, for example, the number of dependent variable observations, 1258. Then we can calculate the standard error of our forecast, so just the sample standard deviation of our error variable, and we have got 1.31%. Then we can calculate the quantile of interest of the said error distribution, so simply calculate percentile.exe of this particular array and then refer to the tau quantile we have just estimated everything for. And it's a good sanity check because if you have applied everything properly, this error quantile should be 0 or at least very close to 0. And that's exactly the case here, which means that our solver algorithm has converged to proper parameter values. Good sanity check always. And now, to calculate the kernel density estimation, would use the robust bandwidth selection algorithm by using both the standard deviation of our error distribution and the interquartile range of our error distribution. Again, the kernel density optimization is simply a numerical algorithm that allows you to approximate probability density of any empirical distribution. Here we have got some errors that we are not really sure how they're distributed, isn't it? And we need to evaluate its density at one point, so kernel density is the best way to go here. And bandwidth is just the optimal smoothness of this particular algorithm. And it depends on how noisy the data is and how large the sample size is. And by selecting an optimal bandwidth, you solve for a bias variance trade-off. If your bandwidth is too low, this estimation is too noisy. If the bandwidth is too high, then it is too biased, too far away from true density. So here we need to just figure out the interquartile range and divide it by 1.34. So interquartile range is just the difference between the 75th and the 25th percentiles. So percentile.exe of your error distribution with 0.75 minus the same function but 0.25, so the difference between the third and the first quartile, and we divide it by 1.34, and we get 0.88%. And now we are ready to calculate the optimal bandwidth as per this formula, how smooth our kernel estimation should be. 0.9 times the minimum of the standard deviation and the interquartile range divided by 1.34, and then we multiply it by the sample size to the power of minus 1 over 5. And we see that our optimal bandwidth is 0.19%. Now, having figured that out, we can apply the kernel density estimation to figure out the density of the error distribution at basically 0 at the quartile of interest to get our covariance matrix down the line. So here, for the kernel observation at a particular data point, we can simply apply some kernel function. And here, obviously, as we're interested in estimating a quantile regression with 1258 observations and 3 coefficients, we cannot resist using a t-distribution, student's t-distribution with 1258 minus 3 degrees of freedom, isn't it? That is quite organic, quite intuitive, given the task we are trying to solve. So here, let's apply the t-distribution, inputting scaled x by the bandwidth. So we just get our x variable we are interested in estimating the density at, which is basically 0, and we lock the row here. Subtract the current value of ith, divide it or scale it by the bandwidth we have just calculated, by h, and we'll lock the row here as well. Then, for degrees of freedom, we input the sample size minus the number of linear restrictions, which is the number of coefficients, which is 3. And then we need to specify that we're interested in density estimation and not in cumulative probability distribution, so we input 0 or false. And then we can bottom-left click it all the way down and calculate our kernel density, evaluate it at 0 by just summing all of those observations and then adjusting by the sample size and the bandwidth. That involves just dividing by n times the bandwidth, as per this particular formula. And we get our kernel density at approximately 47. Now we're ready to estimate the covariance matrix, the standard errors, and test for the significance of coefficients. So here we have got a 3x3 matrix that we can apply. So first of all, we use the inverse of the xt times x. So m inverse of a matrix multiplication of the transposed matrix of the independent variables constant included times the same matrix non-transposed. So we can just copy that and paste it over here. Close the parentheses and close the parentheses again. So xt times x to the power of -1 solved. And we adjusted, multiplied on the left by this particular constant, which is tau, the quantile, times 1 minus tau, and divided by the squared error density evaluated at the quantile of interest. So kernel density squared, and then we multiply it by the inverse matrix. And we enforce this formula using Shift Control Enter and get the covariance matrix estimated over here. In the diagonal of the covariance matrix are the variances of coefficients, so the square root of the diagonal elements are the standard errors we're interested in and can use to test for coefficient significance. So here we calculate the square root of the top left element to get the standard error of the constant. Here we calculate the square root of the middle element to calculate the standard error of the market coefficient, of the beta of the conditional median. And here for the oil coefficient, we calculate the square root of the bottom right element. And finally, we can calculate our t-statistics by just dividing the coefficients by the respective standard errors, dragging it across, and then applying the two-tailed t-test to determine their statistical significance. However, we can already see that the magnitude of those t-stats is so high that they are undeniably significant. However, just to be sure and for good practice, we apply a two-tailed t-distribution, inputting the absolute value of those t-stats and applying the degrees of freedom accordingly. The number of observations with column locked minus 3, where 3 is the number of coefficients or linear restrictions imposed on the data. And we see that those are indeed overwhelmingly significant at 1%, with p-values being very close to 0 and less than 1% definitely. However, the beauty of the quantile regression and the flexibility of the algorithm we've just came up with is that we can change the quantile and do some stress testing. For example, let's estimate what is going to be the 0.1, the 10th percentile of our returns. So what is going to happen on the lower end of our luck? What are going to be the lowest returns of ExxonMobil subject to some realizations of market in oil? And most importantly, do low-end returns, do returns of ExxonMobil when the market is in turmoil still respond to the risk factors? And that is why quantile regression is so important to determine hedging or safe haven properties of assets. I have got a video on safe havens and hedges where I use conditional correlations, but quantile regressions are even a more robust technique to determine that, because if returns of some asset do respond to some risk factors at the lower end of the distribution, for example, a 10th or 5th percentile, it's definitely not a hedge or a safe haven. And here we can check whether ExxonMobil is. Well, it probably isn't, but just for a proof of concept, isn't it? So we can just rerun the solver with the new quantile inputted over here and wait until the results converge. And we can see that, first of all, the constant, the alpha, as you wish, at the 10th percentile is remarkably negative, minus 1.46%. But what is more important is that those coefficients have not changed much. ExxonMobil, at the lower end of the return distribution, still does react to market factors and oil-related factors, meaning that in terms of risk exposures, ExxonMobil is not particularly robust. It is responsive to risk-related factors on the lower end of the distribution, meaning that it is not a hedge. However, for something like gold, you can run that and potentially arrive at insignificant coefficients at the lower end of the distribution, reinforcing the fact that it's indeed a safe haven or even a hedge. Now, let's, just for a proof of concept again, run it for the higher end of the distribution, for the 90th conditional percentile or 0.9th conditional quantile, applying the solver again and waiting for it to converge. And here we see that it's exactly the reverse. Well, coefficients do remain positive and overwhelmingly significant, whereas the constant is now positive and significant, meaning, well, everything goes well. ExxonMobil does have a positive and significant return. And that's all there is for quantile regression estimations in Excel and their applications for stress testing and risk management. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, economics, or finance you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.